let us start. Yeah. So good afternoon, everyone. Welcome to the August mini-school. My name is Francesco Petruccione. I'm the director of NITheCS, and today I have the big pleasure of introducing to you Professor Tjaart Krüger. Tjaart is an associate professor in the Department of Physics at the University of Pretoria, and he did his PhD and a postdoc period at the Free University in Amsterdam in the research group of Professor Ring van Grondelle, who is one of the famous experts in photosynthesis. And there he applied single molecule spectroscopy. So he's been in this game for a long time. Yeah. At University of Pretoria, he established a very nice and growing research group. Yeah. Where he studied, among other things, and I will mention here only the theoretical and computational aspects, yeah, of the investigation of photosynthetic light harvesting complexes, and his work extends in the meantime also to other organic polymers and maybe other nanoscience related topics. Yeah. He's a well-published researcher. He was in the executive management of the South African Young Academy of Sciences. Yeah, so well done for that, Tjaart. Yeah, and he's also one of the senior editors of the Journal of Physical Chemistry Letters. Yeah, and maybe what is also very important that Tjaart has been instrumental in promoting biophysics in South Africa. And I think he chairs the South African Biophysics Initiative, yeah, and many more things that that I don't want to mention now because I don't want to steal too much time from Tjaart's talk. Yeah, Tjaart, we are very, very happy that you're with us this afternoon, and you're already sharing your screen, so you're welcome to start your presentation. And maybe just the usual reminder to the participants, maybe during the talk, make use of the Q&A. There is a button at the bottom of your Zoom screen to ask questions. And at the end of the lecture, you can raise your hand and we can give you the right to ask the questions in person if you wish to do so. Yeah. So Tjaart, now it's... Now, Tjaart, sorry, I didn't notice it. Tjaart postdoc, Dr. Towan Nöthling just joined us, and Towan will contribute to this lecture series. Professor Krüger will give the first two lectures, and his postdoc, Towan Nöthling, will give the last two lectures. Yeah, so I will introduce in detail Towan when it will be his turn to speak. Yeah. So thank you very much, Towan, to you as well for being part of this mini school. Yeah, we are all very much looking forward to learn something about modeling optical spectra. Thank you very much. Tjaart, over to you.
Thank you very much, Francesco, for a very kind, elaborate introduction. And yeah, thank you also for mentioning how I started, and that was on the topic of photosynthesis. So some of the participants might wonder how photosynthesis gets you to the modeling of optical spectra. Well, if you consider the very first few picoseconds of the photostatic process, it has all to do with light-matter interaction. So that is where my interest started. So the very first step of photosynthesis is the absorption of photons from the sun and then the transfer of this energy. And since it is a light-dependent process, optical spectroscopy plays a vital role in understanding what happens during the first few picoseconds, especially of this process. Okay, so this mini-school series is on modeling of optical spectra. It is a fairly broad topic, and this first lecture is also going to give a broad overview of some basic principles of electronic spectroscopy, as you can read here. So here's an outline of the 4 lectures that I will give together with my postdoc, Towan Nöthling. So I'm going to present the first 2 lectures. Today I'm going to present on the basic principles of electronic spectroscopy, and the time is too short to touch on all the aspects, but I hope that I will do justice to talk about some of the most important principles. And then next week, same time, I'm going to give the second lecture, and there I will go in more detail into coupled molecular dipoles, looking specifically at the two different limits of coupling. First, the weak coupling limit, which is called the Forster domain, where you get Forster resonance energy transfer between the two dipoles, and then also the strong coupling limit, where molecular or Frankel excitons are formed. And then the last two lectures will be given by Dr. Towan Nöthling, and he's going to use the principles that are laid, and during the first two lectures, build on them in order to introduce you to linear and non-linear spectroscopy. So the main focus will be on linear spectroscopy, where he will introduce a linear response function and how that can be implemented. And then also some time in the last lecture will be spent on non-linear spectroscopy. Okay, the outline of this lecture, these are basically the topics that I'm going to introduce to you. I'm going to start with the Einstein coefficients. That will lead to the law of Lambert-Beer. So I'm going to derive the law of Lambert-Beer from the Einstein coefficients. That will then lead to time-independent perturbation theory, which I will do quite briefly, just highlighting the most important aspects. For example, the transition dipole moment, which is a key aspect of spectroscopy. Then I'll go to the Frank-Condon principle, look at that briefly, the Jablonski diagram, looking at different competing processes and their rates. And then I will end this lecture with having a brief look into spectral line shapes or line broadening. Okay, I thought this slide is essential. Not all of you might have good pre-knowledge. So I'm going to try to keep the explanation simple, but it will be very valuable if you have had a basic introduction to quantum mechanics, especially if you're familiar with working with bracket notation, because that's what I'm going to use when I explain a time-dependent perturbation theory. And also a basic introduction to classical electromagnetism is going to help. I'm going to base some of the concepts on concepts that we know from electrostatics, and then also look at electromagnetic waves, considering that light is an electromagnetic wave. So looking at the properties of light specifically. Okay, so let's dive into this topic. As a good physicist, let's start with a definition. So I would define spectroscopy as being the study of light-matter interaction, or more generally, the study of the interaction between matter and electromagnetic radiation. But if we consider optical spectroscopy, we consider light that interacts with matter. And as you might already know, light is the visible part of the electromagnetic spectrum, basically the part that we can see with our eyes, or generally taken to be slightly broader than that. So our eyes can see from about 380 nanometers to about 750 nanometers. Often this spectrum, the visible part of the spectrum, if we consider light, is taken to be a little bit broader than that. But it doesn't really matter because light is an electromagnetic wave. And most of the concepts that I'm going to introduce here apply to any part of the electromagnetic spectrum. So they can be used equally well if you consider X-rays, for example, or radio waves, or gamma rays. Okay, so since this is a study of light-matter interaction, quantum mechanics is key to the understanding of this interaction. So quantum mechanics lays the basis, and that's also the approach that I'm going to take. So some of the well-known expressions I would like to derive from first principles so that you can see where they come from. And I also thought it's interesting to just add a bit of the history of quantum mechanics when it comes to introduction of some of the concepts. So you will see some historical highlights also, because the development of spectroscopy is completely intertwined with the development of quantum mechanics. Okay, let's start with just considering the basic processes of interaction of light with a sample. Let's consider this is a sample. It can be any sample that interacts with light. We have some light that is incident. There's a fraction of this light that is transmitted. And the first process that will give rise to a lower intensity of the transmitted light compared to the incident light is that of absorption. So the molecules can interact with the light and actually absorb some of the light. That's the first process. Second process is there can be reflection at interfaces. So I'm not going to consider this process, reflection. I'm going to consider absorption. Scattering is another process. So there are different types of scattering with the dates put here for when they have been discovered. So the first and most common type and dominant type is Rayleigh scattering, where there's no change in the energy of the scattered wave compared to the incident wave. And then there's Meath scattering, which is very strongly size dependent. So it depends very much on the size of the particles. If the particle size is of the same order of magnitude as the wavelength of the light, then the scattering pattern is going to be different from Rayleigh. There would be, for example, more forward scattering than backward scattering, whereas Rayleigh scattering is more isotropic scattering. And then there's also Raman scattering, where the incident wave exchanges energy with the environment. So there's some vibrational modes that interact with the incident light, and that gives rise to inelastic scattering. Okay, so scattering is also a quantum mechanical process, but I'm also not going to look into scattering in this lecture. I'm going to look at absorption and emission. Okay, emission was first described by Sir George Stokes already back in 1852. If you consider a single molecule, then the emission pattern has a dipole pattern. If you have a collection of molecules, then emission is typically isotropic. Okay, let's start with emission. So one of the most well-known cases of emission is that of Planck's black body radiation. So he already derived an equation for this back in 1900, and this was in order to address the so-called UV catastrophe problem. In order to resolve this problem, he said that the energy must be quantized. So this was the first time that the quantization was introduced the Planck's constant here. The H is, has a bar through. Well, H bar is Planck's constant divided by 2 pi. Okay, so by introducing this quantization, he managed to resolve this UV catastrophe, and he calculated the spectral energy density. Spectral energy density, okay, as a function of the incident frequency, and it's also strongly temperature dependent, and here's a depiction of that energy, spectral energy density as a function of the frequency of the light. Right, so I just wanted to highlight this equation, the quantization. Einstein took this a step further by saying that it's the light itself that is quantized, and by postulating this, so the light itself is quantized, the smallest unit of light is then a quantum of light called the photon. He said the light itself is quantized, and he proposed this idea in order to describe the photoelectric effect a few years later. Okay, another very well-known emission spectrum is that of the hydrogen atom, and here you can see the different lines. The so-called Balmer series is as the emission in a visible range, so that can be seen by the naked eye. So Balmer described this back in 1885, and a few years after him, Rydberg proposed an empirical formula in order to describe the exact positions or the exact wavelengths of these Balmer lines. So this was an empirical formula, but then many years later, Bohr described, well, he developed a theoretical model in order to describe the Rydberg formula. And in this model, one of the postulates was that the energy difference between two energies, the difference between two energies must be equal to a photon. So the energy of a photon, h, the Planck constant, divided by the frequency of light. So in other words, delta E, if this is satisfied, delta E is equal to h times the frequency of light, then emission takes place. Okay, and the energy is exactly the energy difference between these two, between the two orbitals. Okay, so this was based on the Bohr model. It is, this Rydberg formula is quite good to describe alkali, but for many other types of atoms and molecules, it does not really work. But in any case, this was really one of the breakthroughs. And again, what I would like to highlight is this equation. Delta E is equal to h times nu, the frequency. Okay, so Einstein built further on this a few years later. Okay, he proposed the so-called Einstein coefficients. He considered a two-state model. So let's consider they are N1 atoms in the ground state, or in a state with energy level E1, and N2 molecules in an excited state with energy E2. Okay, so the process that was already proposed by Bohr, that is the emission. Okay, and it was known that the energy difference between these two energy levels is equal to the energy of one quantum, so h times nu, or we can also rewrite it as h bar times the angular frequency. Okay, so we are on resonance here, so I'm going to use a subscript 0 to define resonance, so resonance angular frequency. Okay, so that was already known. Einstein introduced another process. Well, okay, so this is the rate equation related to the emission process. The other process was when there's an incident field, okay, with a spectral energy density rho, okay, and when the frequency is such that h bar omega is equal to the energy difference between these two energy levels, then a photon from this incident radiation field can be absorbed. Okay, so introduce the absorption coefficient. Okay, and this is a stimulated process because it is stimulated by the incident radiation field, and the associated rate equation is then written like this, where we have the radiation field that is included. So B12 times rho, this is then the rate constant. Okay, so at steady state, these two processes must be equal. Okay, so if we set these two rates to be equal, the two right-hand sides must also be equal. So that's the one equation that we can get. So from this, we can express the spectral density in terms of the two Einstein coefficients and the ratio N2 over N1. And I must just note here that just for the sake of simplicity, I'm excluding any degeneracy. So the degeneracy of both levels are taken to be 1. Okay, so this first equation is based on rate balance, and this second equation follows from statistical mechanics, which at equilibrium, at thermal equilibrium, the ratio between the two, well, between N2 and N1, the number of molecules in the two states, must be equal to the Boltzmann factor. Okay, so from this, okay, we can get the rate, okay, and then we can plug this expression into expression up here. Okay, and that gives us the energy density as a function of the Einstein coefficients and then also this exponential factor. But another expression that must be satisfied is the one that I introduced earlier to you, Planck's radiation law, which is written like this. So this is the spectral energy density, and you can see that the two expressions are the same except for this -1. So that means that there was an additional process that was neglected in this derivation. Okay, and this additional process must also be a stimulated process by the incident radiation field, and there can only be two options. So we've already accounted for one option, absorption due to the incident radiation field. The only other process that can happen is, well, we have only considered absorption emission here, so it must be a stimulated emission process. Okay, and since we have a -1 there, the rate must be identical to that of the absorption process. Okay, so by doing this derivation, Einstein actually discovered stimulated emission. Okay, this was the additional process that must be present with same Einstein coefficients. Okay, so this is then a more complete picture. We have spontaneous emission, it's just a spontaneous process. Then we have the two stimulated processes, stimulated absorption and stimulated emission. The accompanying rate equations are given here. And now at steady state, firstly, now the expression that we can derive from these rate equations at steady state, okay, this now agrees with Planck's radiation law. Okay, and from equating these two expressions, we can now get the ratio A to 1 over B to 1 is equal to that, and these two rates related to absorption and stimulated emission are also equal if we consider a degeneracy of 1. Okay, so that's excellent. So now we have these three processes, and let's go a step further. Now we want to derive an expression for the absorption spectrum. Okay, so let's consider a beam of light moving through a small distance dz, okay, of a medium with a cross-sectional area dA. Okay, so say this is our sample here, cross-sectional area dA. Light travels through it through a distance dz. Okay, the incident intensity is given here as a function of angular frequency and distance. And when exiting the sample, we have a different intensity. Okay, so at steady state, the three rate equations that we had before, when we add them up, they must be equal to 0. Okay, and now since these two coefficients are the same, and well, since this is the case, only spontaneous emission removes energy from the radiation field. Okay, so in other words, the corresponding power that is removed from the radiation field is equal to this. Okay, so I've just added h bar omega there. That depicts the energy of, energy of a photon. Okay, and A21 as the unit of per second. Okay, so we have the power, which is energy per unit time. Okay, so that's the one expression that we have. Okay, and then we can also use this steady state rate equation up here to express A21 in terms of B12, the difference in the number of molecules in the two states N1 and N2, and the spectral density. Okay, that's the one equation that we are going to use. The other one is, if we now consider, okay, so we are removing power from the radiation field. Okay, so in other words, the power absorbed from the radiation field can also be written as this. Okay, and here in blue is the optical cross-section, which is the same for the absorption and the stimulated emission processes. Okay, and then considering that what I have here, I, the irradiance, okay, which is power flux per area. Okay, if we multiply this with the optical cross-section, okay, we are getting a power. I'm now just compensating for the fact that, okay, we are considering all the different frequencies, so we integrate over all the frequencies, and I'm also considering both stimulated emission and absorption, so the two stimulated processes, okay, with the corresponding numbers in the respective states N1 and N2. Okay, so this is the second expression for the power, and now we can equate these two expressions. But before we do that, let's have a closer look at the irradiance, or another term for that is the intensity. The intensity is the time averaged surface power density. So we can write the intensity as the spectral density times the speed of light in the medium. And I'm just considering a refractive index of 1 now, so we can just work with the speed of light in vacuum. Okay, so, and let's also consider resonance conditions. I'm using here omega naught, so we can consider the spectral density. We can write this in terms of the irradiance or intensity and the vacuum speed of light. Okay, so if we then plug this expression into expression 2 and equate 1 and 2, we get this expression. Okay, so we have the Einstein coefficient B12, we have a prefactor here, and then we have an integral. So we are integrating over the optical cross-section. And now if we consider absorption cross-section, what we have here is a measurable absorption spectrum. And this is really fascinating. If you just look at this, on the right-hand side, we have something that can be measured. So it's experimentally accessible. On the left-hand side, we have basically just some mathematical formulation. It's difficult to give really a physical significance to this. But now we have like a theoretical concept and experimentally accessible feature on the right-hand side. Okay, so we can actually now determine this theoretical concept B12 by measuring the absorption spectrum of the sample and just adding this prefactor in the front. Okay, let's use the same expressions, and I'm going to derive the law of Lambert-Beer. So this is a very well-known law, especially in material science and in chemistry. It's very often used when you measure an absorption spectra. Then you use the law of Lambert-Beer in order to derive certain properties about the sample of interest. Okay, so we are considering the same sample here, light that is sent through, and we're going to assume a spectrally narrow excitation beam. And also we will consider resonance condition. Okay, so we can work only with omega naught, both for the intensity or the radiance and for the spectral density. Okay, so if we do that and we just plug these two into the expression on the previous slide, we have this power, okay, the power that is removed from the incident radiation field. So we send a beam of light in, there's some power that is removed from this light due to interaction with the sample. So this is the amount of power that is absorbed from the incident light beam. It can be written like this. Okay. If we consider the spectral energy density, so if you just think about this term, the spectral energy density, okay, we can relate it directly to the power. Okay, because power is energy per unit time. Okay, and the spectral density, we are considering a three-dimensional volume. Okay, so we have to multiply with delta V, so a unit of volume, in order to convert this spectral energy, spectral energy density to a power on this side. Okay, and since a light beam is moving through the sample and it's losing energy, okay, so the spectral energy density changes with time and it's a negative rate. So that's the reason for the negative sign there. Okay, so let's now convert that time-dependent change in the spectral density to a distance dependence. Okay, so I'm just converting the 1 over dt to c over dz. Okay, and then we're making use of the definition of the irradiance that I introduced in the previous slide. Okay, in order to replace d rho times c with di. Okay, di is just the difference in the intensity or the irradiance before and after passing this distance dz. Right, so now we have two expressions for the power that's absorbed from the radiation field. This expression here and the one here. So by equating the two, we get the expression down here. Okay, let's rearrange the terms. Okay, then we can recast this expression into this form. Okay, let's now integrate both sides. So now we have the intensity as a function of position z, okay, is equal to the intensity before the light hits the sample. So the initial intensity is the amplitude here, the first term, and then we have an exponential there. Okay, let's consider an absorption process. So for such a case, N1 is going to be much greater than N2. So in fact, one can use the same expression to describe a process, for example, lasing process that describes a laser, the formation of a laser beam. In that case, you have population inversion, in which case N2 is greater than N1. But let's now assume that N1 is much greater than N2, so absorption is going to dominate. And then N1 minus N2 over a unit volume, that is then the number of molecules inside the beam path that will be excited. Okay, so this expression will then be approximately equal to this one if absorption dominates, and this is one form of the law of Lambert-Beer. Okay, but we have expressed it now in terms of the absorption cross-section, for which one commonly uses a base of the natural logarithm, so e, base e. But normally a different absorption coefficient is used. and that is called the extinction coefficient, for which base 10 is used. Okay, so if we then make this conversion from base E to base 10 in order to use the extinction coefficient, and we also convert the number of molecules to the concentration, then we can express the extinction coefficient in terms of the absorption coefficient, and we can rewrite this expression in this very familiar form, very compact form, which makes it a very elegant equation. So this is the familiar form of the law of Lambert-Beer, where OD stands for the optical density, and that is the extinction coefficient times the path length. So if we integrate over the full path length, the light traversing the sample times the concentration. Okay, let's get to the physical basis for light absorption. So the physical basis can basically be defined as the interaction between the atom or the molecule's electronic charge distribution and the electric field of the light. Okay, so remember, light is an electromagnetic wave, and we are considering only the electric field component. That's a component that interacts with the electronic charge density or charge distribution of the molecules. Okay, and here we can learn a lot about this interaction by considering electrostatics. So let's consider a molecule's electron cloud with a continuous volume charge density rho. So don't confuse this with the spectral density introduced before. This is now something completely different. It's the continuous volume charge density of the molecule. And this generates an electric potential at R. Let's say this is a molecule, generates an electric potential here at R, position vector R, given by this. Okay, let's now do a Taylor series expansion about R prime equals to 0. And we can do that if R, small r, the position vector, is much greater than the typical dimensions of the molecule. Okay, let's approximate this as a sphere with the radius capital R. If this condition holds, we can do a Taylor expansion of 1 over R minus R prime. Here are the different factors, the different components. Okay, and if we plug this expression into this one here, these are the different components that we get. Okay, and here the Q, mu, capital Q, all of them are called the multiple moments of a charge distribution. So Q is the electric monopole, mu is the electric dipole, we have the electric quadrupole, and so we can get to higher orders. Okay, so if we look at the first term here, this is simply the Coulomb potential describing a charge. Okay, so if our molecule has a charge, then this component will become important, but in most cases we consider non-charged systems, in which case the second term is going to become a dominant term. So this is, for this term, we consider the electric dipole, but even if the system does not contain a permanent dipole, I'm going to show you that due to the interaction of the electric field of the light, this term is still the dominant term. Okay. For a complete model, it's prudent to also take into account, say, that the next term, so some of the higher orders, but in most cases, the second term is the sufficient one. Okay, let's now have a look at the interaction with the electric field. And yeah, let's again consider electrostatics. We consider an electrostatic scalar potential that generates this electric field. And this expression is simply the Poisson equation. Okay, so when this electrostatic potential interacts with a molecule's charge distribution with this potential, then we get this potential with all these different terms. Now, in the case of light, the first term is going to be 0, obviously, and the second term is by far the dominant term. So this is a term that we are going to use. Okay, and we can use time-dependent perturbation theory using this potential. Okay, and our perturbation Hamiltonian is then exactly this second term that we are going to use to describe the perturbation of the electronic cloud density due to the interaction of the electronic cloud with the electric field of the incident light. Okay, So this interaction causes a small perturbation. So this is exactly the perturbation we are considering. And we are considering an electric dipole in general. But as I'm going to show you, even if this system doesn't have a permanent dipole, a transient dipole is going to be formed due to the interaction with the electric field. And this is what is responsible for absorption and also for emission. We can use the same theory to describe emission. Actually, very similar theory. Okay, so as I said, we can use perturbation theory, and then since we are considering time-dependent potentials, we must account for transitions between energy levels. So in other words, we consider time-dependent potentials, so we are going to use time-dependent perturbation theory. Okay, so let's consider a molecule with discrete energy levels and a complete set of orthonormal wave functions interacting with the beam of light. Right, so if there's no light present, then this time-independent Schrödinger equation completely describes the system. So we have a complete set of orthonormal functions, and they satisfy this Schrödinger equation. So we can calculate all the different energies, okay, and you have the Hamiltonian that describes the system. Okay, this is trivial. This is the case for the light that is off. We are interested, as we said, with light on, light matter interactions. So in that case, we have to consider the time-dependent Schrödinger equation, and we are considering the perturbation Hamiltonian, and we have now an unknown wave function. But since we've said that for this equation, we are considering these states to form a complete set of solutions, we can express our unknown wave functions as a linear combination of all the known wave functions. Okay, so we do that, and then following a normal process, so I'm just now going to use bracket notation just in order to simplify everything. So for those unfamiliar with this, okay, so I've put the H prime here. This is the interaction Hamiltonian, and it basically describes the transformation of the state N to the state K. So in other words, it describes the transition from state N to state K. Okay, and this is the rate of the coefficients CK that we can express as a linear combination between all these terms. Okay, so this perturbation Hamiltonian, well, it is due to the incident electric field, and it basically mixes the different states. And due to this mixture between the states, it becomes likely for a transition to take place to another state. So I'm going to explain this in a bit more detail in a minute. Okay, just in order to derive this expression, we have assumed this to be true. I'm not going to go into more details about that, but it generally just depends on the symmetry of the wave function you are considering. So generally for symmetric and asymmetric wave functions with respect to some coordinates, this expression does apply. Okay, let's assume also an instantaneous transition. Okay, then our probability amplitude CK can be written in this form. Okay, so this tells you that at time t prime, this transition takes place from state N to state K, and we are going to make this while considering a long enough process. So start at time 0 and look at a long enough time just to make the probability high for this transition to take place. So t is not going to be infinite. That's going to work counter to what we would like to do, just because of process of Rabi flopping, which I'm not going to go into now, but we're just making t long enough to make sure that the transition takes place at the time t prime. Okay, so here's the expression for the perturbation Hamiltonian that I've introduced on the previous slide. So if we plug this expression in here for the perturbation Hamiltonian, we get this expression. Okay, so what we have here in blue is called the transition dipole moment. Okay, so what is the transition dipole moment? It is the electric dipole moment, because that is what you have on the inside. I've forgotten to put a hat on there, because that is the operator that transforms state N into state K. So this electric dipole moment is associated with an electronic transition from state N to state K. Okay, it is a transient state. It's a transient dipole moment due to the fluctuation of the electron density because of the incident electric field of the light that is just distorting this electron density. Okay, so because of this distortion, a transient dipole moment is formed even in a molecule that does not have a permanent dipole. Okay, and this gives rise to a non-zero probability that the state that transition will take place from state N to state K. A nice way to illustrate this is, let's consider the 1s state, say hydrogen 1s. This is a ground state of hydrogen. Okay, say that an electron is in this state, in this orbital, when the light beam is off, so when there's no light matter interaction. Now, if you send light through this atom, the electric field is going to displace the electrons. So when you have the positive amplitude, the electrons are going to be repelled to one side. For the negative amplitude, the electrons are going to be repelled to the other side. So as a function of time, what you're going to see is a fluctuation of the electron cloud up and down. And this gives rise to a transient P-like state. Okay, so in other words, what this incident electric field has done is to make a 1s state look more like a 2p state. And that's the very reason why this transition from 1s to 2p is a very likely transition to take place due to an incident electric field. Okay, so let's now consider plane polarized light. So let's consider, for example, a case, for example, like this, where the light is propagating along the positive x direction. We have the electric field along the positive y direction, the magnetic field along the positive z direction. Okay, so we can describe our plane polarized light like this. Okay, we have the oscillating component and we have the electric field amplitude that describes the polarization of the light. Okay, so if we plug this into this expression that we've derived 2 slides back, then we get an expression like this. And I've now taken into account that the transition dipole moment is not aligned to the electric field, but there may be an angle theta between the two. So that is a cos theta term that we have here to account for the dot product between the transition dipole moment and the electric field. Okay, and we have here the time oscillating term, and we have the transition dipole moment. Okay, when we are close to resonance, we may invoke the so-called rotating wave approximation, where omega naught, the resonance frequency plus some other frequency, is much greater than the difference between the two. Okay, in that case, we can get a simplified form of the probability of a transition from state N to state K, which is the modulus squared of our probability amplitude, and it is written like this. Okay, so this is a full expression defining the probability of a transition from state N to state K. Okay, and here it is depicted as a function of the frequency, angular frequency, and as a function of time. So as a function of angular frequency, you get a sinusoidal pattern. As a function of time, the closer you get to the resonance, okay, the higher the peak will be. Okay, so at resonance, as a function of time, this peak increases actually to infinity if t is long enough. Okay, but perturbation theory breaks down if t is long enough. So if we make t reasonably short, then we will get a probability that does not really exceed 1. Or well, if you consider an exact process, exact theory, then p is never going to exceed 1. Okay, so a probability of 1 for this transition from state N to state K. Okay, this is the case for monochromatic light. So if we consider only a single resonance, so a single frequency. Let's now consider an energy density. Okay, so we get back to our energy density rho, And now we're going to integrate this probability over a band around the resonance frequency for isotropic incident light. So if we do that, we get the following transition rates. Okay, if we now start in a ground state and absorb a photon with frequency omega naught, okay, so this means we start in ground state, n is equal to 1. We simply plug in for n equals to 1, we get this expression here. So this is the probability of absorption from the ground state to state K. But you might recall that this is exactly how we have defined the Einstein coefficient, well, the Einstein transition rate, okay, where we have the Einstein coefficient times the energy density. So this expression is exactly equal to this transition rate that we've defined before. Okay, so in other words, we can now rewrite the Einstein coefficient for absorption in terms of the transition dipole moment squared. Okay, which is also remarkable. Okay, so now you can see that, okay, we are simply introducing different different factors which are all describing probability. So it actually makes sense that they all must be related in some sense. Both the Einstein coefficient and the transition dipole moment are rather theoretical concepts. Okay, well, transition dipole moment, we can get a pretty good physical understanding, but it's still a theoretical concept. But since we have managed to relate all the Einstein coefficients to the absorption spectrum, like what I've shown here, we can also relate the transition dipole moment to the absorption spectrum. So again, relating a theoretical concept to experimentally accessible spectrum. Okay, and yeah, what I've written here is just that the transition dipole moment is directly proportional to all three Einstein coefficients. Right, I would like to introduce you now to molecular vibrations, not because I would like to work out complete theory for vibrational spectroscopy. We are still dealing with optical spectroscopy, which is based on electronic transitions. For the vast majority of systems, we are considering only electronic transitions. But when we consider electronic transitions, molecular vibrations play an essential role in also describing the probabilities of transitions. Okay, so here are the 6 types of molecular vibrations that's known for molecules consisting of at least 3 atoms. If we consider a molecule consisting of 2 atoms, so a diatomic molecule, then we have only this symmetrical stretch molecule, okay, which I'm going to focus on in a bit more detail. But all these different types of vibrations can be described fairly well in terms of a quantum harmonic oscillator. Okay, so we can consider actually our electronic energy to be represented by this quantum harmonic potential, and all the different energy levels here correspond to the different vibrational modes. So from the lowest energy vibrational mode up to the highest modes. Okay, so this is a quadratic potential, and the solutions are all equally spaced. Okay, this is only a good approximation if we are at low energies. A more realistic potential is a so-called Morse potential. Okay, so here it's shown for the diatomic molecule where the anharmonicity is accounted for at higher energies, and this also takes into account bond breaking at high enough energies. Okay, so what you see here is the energy, well, on this side also the energy as a function of the internuclear separation. So obviously if the atoms are too far apart, then the bond between them is going to break, and you will get, and this happens at the dissociation energy. Okay, so this is a semi-empirical formula that is actually not used very much, but it was the inspiration for a few more useful expressions that are used these days. And yeah, one of the most common ones is the Lennard-Jones potential, okay, where the first term describes the repelling potential between the 2 atoms, well, 2 or more atoms, and here the second term is then the attractive term. So a very common potential is the so-called 12-6 Lennard-Jones potential, okay, where the repulsion part is this part, okay, the 2 atoms are going to repulse each other if they get closer to the equilibrium position, which is depicted here. And then you have the attraction part on this side, which scales with r to the, or 1 over r to the 6. Okay, so this potential is commonly used in force fields and many other applications of computational chemistry. Okay, so yeah, I just wanted to introduce this to you to say that this is commonly the shape of the electronic potential that is used for the ground state energy and for higher excited states. Okay, now I want to get to the Frank-Condon principle. So I've introduced the transition dipole moment to you. Let's just consider the electronic dipole, or actually the dipole consisting of an electronic part and a nuclear part. Okay, and I'm just going to consider discrete charges here. So we are summing over all the different positions. So for the electrons, the first term, and for the nuclear positions, the second term. And now if we want to calculate the transition dipole moment, okay, we are again putting the dipole moment between the bra and the ket. And here, just for the sake of more completeness, I've accounted for both an electronic state, vibrational state, and also a spin state. Okay, so these are all independent, so we can separate them. So the first term becomes this. The second, the first term relates to the electrons. The second term relates to the nuclei. Okay, because the electronic states are orthogonal, this becomes 0. So this full second term becomes 0. So that can be ignored. And we can only consider the first term here. So what is in blue here? So the probability of a transition is dependent on the so-called Laporte's orbital selection rules, okay, which are a set of rules that will determine the probability, or say whether some transitions are allowed or forbidden. The second bracket here is called the Frank-Condon factor. And the first one depends on the spin selection rules. So the second one here, the Frank-Condon factor, tells us that we must consider the overlap between the vibrational states of the two electronic states that correspond in a transition. Okay. So let me depict it like this. So let's say that we are considering an absorption from ground state, energy E0, to first excited state with energy E1. Okay, so the probability of this transition will, well, that is directly proportional to, well, actually the Frank-Condon factor modulus squared of that. But we have to consider the overlap between the vibrational states, so this vibrational state here, and say the vibrational state nu prime equals to 6. Okay, so the overlap between those two states, that will determine the probability of the transition. But similarly, there will be a probability of a transition from this ground vibrational state to many of the other vibrational levels. Okay, and the probability of each of these transitions is depicted by the Frank-Condon factor. Okay, due to this Frank-Condon principle, we get the so-called mirror symmetry between absorption and fluorescence. Okay, and that is just due to the nature of the fact that we can approximate this by a harmonic oscillator, fairly equally spaced energy levels. So you get that the probability of, for example, transition from 0 to 6 will be more or less the same probability from 0 in the excited state down to the 6th vibrational level, and so on. Okay, and the energy difference that is depicted here on the next slide. Fluorescence normally takes place from the ground vibrational state. Okay, so you first have some relaxation along the solvation coordinate. Okay, and this is due to interaction with the environment. So normally vibrational modes that will take place that will interact with the molecule of interest. Okay, so the system relaxes to the ground vibrational state, and then it will relax to the ground electronic state, and then you again get relaxation to the ground vibrational state. Okay, so due to this energy difference between the absorption and the fluorescence, okay, this is called the Stokes shift. So the fluorescence peak is going to be redshifted compared to the absorption. Okay, and I see I'm running out of time, so I think I'll just make a few remarks about the last few concepts. Jablonski diagram as something else I wanted to introduce. So this is the potential as a function of the internuclear separation, depicting all the different photophysical processes that can take place after absorption. Okay, so if you excite a molecule, okay, you will populate some excited electronic state. Okay, and then there can be non-radiative transition, okay, due to, again, interaction with the environment. So exchanging energy with some phonons. Okay, this is called internal conversion. So that's a process I've explained just now. So relaxation to the lowest vibrational state from where fluorescence takes place. Another competing process is intersystem crossing. And that is where spin flipping takes place. Okay, and since there are three states with the same energy, okay, this state that's depicted here, okay, is called a triplet state. So it's triply degenerate, okay, and it's a due to spin orbit coupling, this transition can take place and it can relax again, but it's a relatively slow process compared to fluorescence. Okay, so the energy is normally much lower and the lifetime is much longer, and the radiative process is called phosphorescence, relaxation from the triplet state down to the electronic ground state. Okay, I think maybe just for the sake of time, let me skip the theory that I wanted to introduce here for the spectral line shapes, and I'm just going to get to the summary slide for this. Okay, so there are many different processes that broaden lines. So if you consider instantaneous absorption, one would expect an infinitely narrow line shape of both absorption and fluorescence and all other processes that are taking place. But due to many different processes, you get line broadening. Okay, so these give rise to different line shapes. The first process is called the natural broadening or lifetime broadening or uncertainty broadening. Okay, and yeah, here's the theory for that, but I'm going to skip it, unfortunately, for now. If anyone is interested, you're most welcome to get back to me and I will explain this to you later. Okay, the second process is called collisional or pressure broadening. And this doesn't only take place in fluids like liquids and gases, but it can also take place in solids due to exciton-phonon interaction. So this is also an important process, even for solids. And yeah, here's a description of that. I'm also going to skip the theory in the interest of time. So here's a summary of the most important line shapes, or at least the ones that we are going to consider in this series of lectures. So the first two types of broadening give rise to a Lorentzian line shape, and they result from homogeneous processes. So if all the molecules or all the constituents of the sample of interest experience the same type of interaction, this is an homogeneous process, and the resulting line shape is Lorentzian. In contrast, when different molecules will experience different interactions, different environments, this is called an inhomogeneous process, and the resulting line shape is a Gaussian line shape. And this is the case of Doppler broadening, for example, which is very important for liquids and gases, where the Doppler effect has to be taken into account. Another process is called proximity broadening, and that is when each atom or molecule or constituent of the sample of interest experiences a slightly different environment. And that can be because of, well, that's mostly because of intermolecular interactions, so that you get a distribution of environments that is experienced by the different molecules. So you get different local refractive indices. Okay? And because this is an inhomogeneous process, the result is that you get Gaussian line shape. And this is in most cases the dominant process. So in most cases, line shapes are approximated by Gaussian functions just because of this process of proximity broadening. And then the last type of broadening I would like to introduce is what I would call row vibrational broadening. And that results directly from Frank-Condon principle. So if you remember this figure that I've introduced here, so there are usually different simultaneous transitions that can take place due to the Frank-Condon factor being non-zero for different transitions. Okay, and on top of the vibrational states, we also have rotational states leading to additional broadening. So the effect of all of this, the combined effect is that the electronic transition is significantly broadening by means of simultaneous transitions to different vibrational states and different rotational states on top of that. And then the last very relevant source of line broadening is that of the excitation source. So it's very rarely that an extremely narrow laser beam is going to be used. So these days you get laser beams with line shapes of the order of a wave number or even less. But in general, a line shape of a finite size, say of a few nanometers or even more, is used. And in general, most lasers have a Gaussian line shape, Gaussian as a function of frequency. So that obviously also plays a role in broadening the absorption bands or the emission bands that are considered. Okay, so what we have learned in this lecture, I've introduced you to all these different concepts, and along the way also derived relevant equations. We looked at the Einstein coefficients, the law of Lambert-Beer that was derived directly from the Einstein coefficients. We had a brief look at the time-dependent perturbation theory, introduced you briefly to the Frank-Condon principle. We had a brief look at the Jablonski diagram, and much of spectral line shape theory I had to skip, but I gave you just an overview of that, different processes that take a role there. So that was the focus of today's lecture. In the next lectures next week, same time, I'm going to introduce you to coupled molecular dipoles, strong and weak interactions. The last two lectures are going to be given by Dr. Towan Nöthling. So thank you very much for your time and interest, and I'm looking forward to see you back again next week. So if you'd like to contact me, here are my contact details, email address. You can also follow me on Twitter. And yeah, I would love to answer any questions from you. Thank you very much.
Sorry, Tjaart, I was on mute. And here I come again. No, thank you very much, Tjaart, for the fantastic lecture. We have still some time for questions. I think everybody was very well behaved and didn't ask anything in the Q&A. So I'm not sure if people would like to raise their hand now and ask Tjaart a question in person. You're welcome to do so. Maybe while people think about questions, and please don't be shy. Yeah, Tjaart, will you make the slides available?
Definitely, no problem.
Then we can if you email them to me or Rene, we can post them on the NITheCS website next to the link to the video that hopefully by tomorrow, the day after tomorrow, will be online as well. Yeah.
Yeah, definitely. I mean, there's nothing that I need to keep secret. I mean, what I've explained today is information that is almost a century old. So it's not something
excellent. And that's you know, it's very nice that you say that nothing that you say is a secret, because I want to use this opportunity to promote again the fact that NITheCS is a big supporter of open science. Yeah? And all we do, we want to make openly accessible. We promote the use of open source software as much as possible. And so on and so forth. So it's really, that's why we try to record everything, make it accessible. If we have access to the slides, we put them on the website as well. for ease of reference. Sometimes in the slide, there are references that one might not manage to write down during the talk, so that to give everybody the opportunity. Oh, okay, here comes the raised hand. And I will allow Christine to talk. Christina, you're welcome to ask your question.
Thank you very much. Thank you, Tjaart. I enjoyed your lecture. It's always nice to have a recap of that. I just wanted to ask, are you now generally thinking of molecules in gas phase, or are you thinking towards molecules in a liquid phase, or and what difference does it cause in which phase it is?
Yeah, thank you, Christine. Yeah, thank you for attending the lecture and asking this question. Yeah, I'm not really an expert on gas phase samples, so I hope that I'll give the right answer. What I immediately think about is, especially when one considers the line shape functions, they obviously the type of phase plays an important role determining the types of interactions. Yeah, well, types of interactions, of course, well, molecular interactions, that will more be the focus of the second talk, although I won't really look at well, I won't have an exhaustive discussion of different molecular interactions or atomic interactions, but just look at coupled dipoles in the context of light matter interactions. Yeah, well, for this lecture, I just wanted to give a broad base. So that's why I also tried to make the explanation applicable to samples of any phase, whether it's a solid, liquid, or gas. But in general, as you might know, I'm not really focusing my research on gas phase systems. So yeah, it's mostly, let's say, condensed matter and soft matter systems. So
okay, thank you, Tjaart. Yeah, I think what you've said is very general. One can use it in general, but yeah, the details probably comes in with the line shape and the line broadening.
Yeah. I think that's the main difference. But yeah, I would invite you to give a similar lecture on gas.
I haven't worked on molecules for some time.
We can organize that, no problem. Christina, you're more than welcome.
Okay, but thank you very much for the lecture.
Excellent, thank you. Tjaart, I don't see any other raised hands and any other comments in the Q&A or in the chat. So that's probably a testimony of how clear your introductory lecture was. So thank you very much again from my side, on behalf of the participants. Here come the comments in the chat. It was a very interesting talk. So thank you very much for that. And please join us again next Wednesday. Same Zoom link, same time, 2 p.m. Wednesday afternoon. And if you have nothing better to do this afternoon at 5, let me use this opportunity to advertise a colloquium that is off the usual written. Yeah, usually they're on Monday afternoon. At 5 p.m., we have a talk by Professor Matthew Bales. The title is A Virtual Tour of Einstein Universe. And Professor Matthew Bales is very famous because he discovered the fast radio bursts. Yeah, so he will give a very interesting talk, in particular stressing what role the meerkat and the SKA will play in the future discoveries in astrophysics and astronomy. Yeah, so please, to register online, just go on the on the NITheCS website and register for the talk. We will send you the Zoom link. If you are in Stellenbosch and surrounding, you're welcome to come to the NILSI where the talk will take place. Yeah. So thank you very much, Tjaart. We will see you again next week. And we're already looking forward to part 2 of this mini school. Thank you very much. Thank you.
Yeah, thank you very much, Francisco. Thank you, everyone.
Bye. Bye-bye.